Hey everyone, so we are going to look at angular momentum, right? We're going to split this up into three parts. First, we're going to look at just angular momentum of rigid bodies and point masses. Then we will look at the equivalent of impulse for angular stuff, as well as conservation of angular momentum. All right, so let's get into it. So the first part, right, we'll talk about angular momentum of a rigid body. All right, so a rigid body can be any solid object. All right, so we're talking like a disc, a wheel, a can, a CD, a pole, a sphere, any of that kind of stuff. So we define angular momentum with the variable L. All right, this is our variable. All right, and this is equal to I omega. All right, so we had our linear P equals mv. So it's pretty similar in a lot of ways to that, right? The variable we use for it seems to not make sense. And then you have I as your rotational inertia, and you have omega as your angular or rotational velocity. All right, has some interesting units, right? Because the units for I are, if you remember the equation, I is mr squared. And so the units would be kilogram meter squared. And for omega, right, omega is a rad per second. And so the units for L, or angular momentum, are going to be kilogram meter squared radians per second. Okay, kind of a strange unit, but it is what it is. And it is a vector. Okay, angular momentum does have direction. All right, so this is for a rigid body for any rotating regular solid object. We can also talk about a point particle. So a point particle is like a single mass. Okay, you can think of a planet around another planet. Okay, or the sun. The key is it's a single object or point mass, we like to call it, around an axis. Okay, so if you think about the sun, like we call this the sun, and this is our mass, call it Earth, right? This is going to rotate around this guy. This one would have a linear momentum as well as a rotational momentum. All right, and if you look at this, we can think of this basically as a like a donut, okay, or a hoop or a ring. And so the I for this would be just mr squared. And so if we look, right, we said that L is I omega. I is then going to be, mr squared. And omega we know, right? If we rewrite our linear momentum like this, r omega, then we can get our angular as v over r. We'll make that uppercase. And then we could start to get rid of some stuff. And we'll see that L, our angular momentum, is just mRV. Okay. Angular momentum for a point mass. Now, from this, you'll also see, right, that we have a m and a v. And so we know what m and v is from our old equation, P equals mv. And so we can also write that angular momentum of a point particle, or in general rather, is just rp. Now this is really a cross product, but we don't need to be concerned with that in this class. We can take it right from this stage. Right, so we have two parts here that we can look at now. The key here is that you can take a single point particle and take its linear momentum and change it over to angular, and you can take an angular and look at the linear, and then we have it for a rigid body as well. So we can actually do a problem with this now, right? So a frisbee with a rotational inertia of 3.7 times 10 to the fourth kilogram meter squared has an angular velocity of 1.15 rads per second. What is the object's angular momentum? All right, so we know that angular momentum is just I omega. All right, frisbee is a solid or rigid object, right? In fact, it's a disk, so I would be 1/2 mr squared, roughly, right? It does have the lip at the end, but in either way, I is given to us here, so what we can do is we just simply have to take our I and substitute it in, 3.7 times 10 to the fourth. We'll put in our units, kilogram meter squared, and our omega is given to us 1.15 rads per second. And so you can just take 1 second and go ahead and give this a try. And what you should see is your angular momentum should come out to 42,550 kilogram meter squared rads per second. All right, so we can move on to our next one. All right, in this case, we have a single 50 kilogram person who is running around a circular track of radius 30 meters. All right, if the person has a speed of 6.2 meters per second, we want to find two things: what the person's linear momentum is, and also what the person's angular momentum is. So for linear momentum, we just have to go back to our old way of doing it, right? P equals mv, right? Don't forget about momentum. All right, we can find our mass. It's just a 50 kilogram person. And we have our V, which is just 6.2 meters per second, right? This is a linear or a tangential speed. So if you think about the person running around a circle, right, wherever they are, great drawing, right? They're always running tangent, at least if they're trying to run on the outside of the circle. And so we can take a second to solve this. And you should see that your momentum, at least the linear momentum, is going to come out to 310 kilogram meters per second. Okay, so now what we want to do is we want to get the angular momentum, and there's a couple ways we can do this now, right? So we know that L is equal to I omega, or we know that L is equal to mvr for a point particle, or L is equal to rp. And you'll see all three of these are the same, especially because I is just equal to mr squared in this case. All right, you have that hoop again. And so we'll take this one off to the right because we already found what P is. And so the angular momentum will just be 30 meters times our original, or our linear momentum. All right, and then you can solve this. And we get 9,300 kilogram meters squared per second. Now you'll notice that this does not have radians in it like our previous one did, but that is okay, right? Radian is just a kind of a placeholder so we know what units we are working with. Yeah, and so all right, radians everything in terms of pi. So that's really the key to that. So that's basically it in terms of the intro for angular momentum. It's basically momentum for a rotating object.